Thank you, Peter. So yes, I'm going to talk about explainable AI and namely about the use of logic in explainable AI. So before we start, I should say that this is not just my work. So this is done in cooperation with a number of people, including João, Nina, Peter, and others. And I should also say that while I borrowed some of the slides of my colleagues, quite a bit of them. So today I'm going to talk about some of these topics. So this is a mind map on reasoning for trustable or formal XAI. So I will briefly talk about interpretable models. I will also briefly talk about trustable explanations, how to compute them using logic. I will mention how to reason about heuristic explanations and show if they're sound or not. There is another orange area which is not covered in my talk today, but it exists. So there is a tight relationship between machine learning verification and also fairness on one side and explainability on the other side. This is left uncovered in my talk because of the time issues. So let's start with a bit of motivation, what explainable AI is and why it is important. Right, so we all know that we've been living in the era of machine learning revolution. We are all surrounded by our smartphones, which have smart assistants. We all know about the successes of self-driving cars and autonomous vehicles in general. There are huge successes in computer programs based on machine learning that can outplay humans in hard games like Go and chess. And there are, of course, robots that come into reality and they are supposed to help people in their homes and also in hospitals. But on the other hand, there are lots of issues in machine learning. First of all, they are brittle. They are known to be easily breakable. Second, they exhibit a lot of bias. In the decisions they make, there is a lot of bias. And finally, nobody really understands how they work and when they fail, if they fail, what to do. Okay, so this brings me to the need for explainable AI. On this slide, I would like to show you a complicated abstract machine learning model. It can be a neural network, it can be anything, and say it's trying to distinguish animals. For instance, it receives this picture of a cat and it says it's a cat. Okay, and in the current status quo, what we get is just the prediction. It says it's a cat and that's it, nothing else. In reality, as users, we would like to get an explanation why it is a cat. What features of cats are present there in the picture that make the system conclude that that's a cat, right? In the ideal world, we would like to get an explanation in the form of some high-level features saying this is a cat because it has intrinsic properties of cats like fur, whiskers, and claws. So why XAI is important? Well, in 2016, European Union released this large document called General Data Protection Regulation, and in that document there are a number of requirements on automated systems. One of the requirements is the right for explanation. Here is a quote: "When put into practice, the law may also effectively create the right to explanation whereby a user can ask for an explanation of an algorithmic decision that significantly affects them." Right? The United States are also extremely interested in explainable AI, and the existence of this high-profile DARPA program on explainable artificial intelligence underscores this fact. Moreover, in 2019 in the US, there was an attempt to legislate Algorithmic Accountability Act, so that would force companies to check their algorithms for bias and transparency. More recently, in EU, European Commission, together with the special expert group on AI, they released this huge document on ethics guidelines for trustworthy AI, where they define what an explanation is, under which circumstances a user may want to get an explanation, and in which form. And I guess if I Google any similar document in any country, I probably will manage to find some. But since most of us are located in Australia, so I just Google if there is something similar in Australia, and yes, there is. So there is this quite a large document. It's available online. It's Australia's Artificial Intelligence Ethics Framework, and there are a bunch of principles listed there, ethics principles, and of course one of the principles is the principle of transparency and explainability, where they also define what explanation is, who is the user, what kind of explanations are necessary, and when. So to conclude this motivation part, explanations are necessary in situations of high-risk applications, for instance, in biometric identification and categorization of people, in law enforcement, if it involves AI-based decisions in banking, and of course in safety-critical applications, for instance, in healthcare or self-driving cars. If something bad happens, if a wrong diagnosis is made, or if a car hits a human, then it can cost that human a life. We don't want that, right? So the problem generalizes to autonomous vehicles in general. And XAI is not only important, not only explanations are important, but correctness of explanations is crucial. Because explanations, if they really reveal what is happening inside, what is the logic that is behind the automated system, why it behaves one way or another, it can help us build trust in the AI systems. That's one thing. Another thing is that if we trust explanations, if they reveal issues or they prove that there is no issue, they can prevent accidents. And if something bad happens, we can try to debug an AI system and maybe certify it. Okay, at this stage, I should say that there are two major approaches to explainable AI. The most prominent approaches include interpretable ML models, where people try to compute, to use these models. These include decision trees, decision lists, and decision sets. And probably the most popular approach is to compute explanations on demand, given a decision made by a black box machine learning model like a neural network. So I will talk about both of these briefly in my talk. Okay, let me start with interpretable models. So interpretable models are based on rules, and each rule is of the form if-then. Because of this, the rules are deemed to be transparent, so they're easy for us humans to understand. We humans understand conjunctions pretty easily, and that's why these models come in handy in explainable AI. So as I mentioned before, there are three major models that are deemed interpretable. These include decision trees, decision lists, and decision sets. There are others, for instance, BDDs or other classes, families of graph-based classifiers, but these are the most popular ones. Okay, here I have a couple of examples. Say we have a data set called Titanic. It's a well-known data set. It lists individuals that traveled with Titanic. We all know what happened. And each instance in the data set, in the table, each row, it lists the attributes of the individuals that traveled with Titanic. For instance, their class, passenger of first class or crew, their age, their gender. And the idea is that we train a model that predicts who survived and who didn't based on their features, right? On the left, we have a decision tree. On the right, we have decision list and decision set. The difference between decision list is that the rules are ordered. So the order is important. You first check the first rule, if it applies or not, then the second, and so on and so on. In the decision set, the rules are not ordered, so you can pick any rule that applies given your instance. And let's dive into details a bit. So we assume the standard classification scenario here. Let's say we have this table, this data set, and this concrete data set is used to predict whether or not our friend is going to go on a date with us, depending on various circumstances. And this is a valid decision set that is trained on this data set. So this is an ordered set of rules. Each rule is in the form of if-then. And the idea is that the model we get, it must respect the training data. So it should behave exactly the same way, or at least it try to behave exactly the same way as it's written in the data set, but it should also generalize well enough, right? So if we have some unseen data, we should be able to predict more or less correct outcomes, even though those instances are unseen, right? And of course, since we're humans, we understand only small pieces of information, so it's better to have some small model. The smaller the better, because it makes the model interpretable. On this slide, I have a pseudocode of the standard logic-based approach to the problem of learning such a model. And the model can be a decision tree, a decision list, or a decision set. It doesn't really matter. And there are various approaches that are based on logic and constraints, but this is the main typical skeleton. This is a loop, and the main parts of the loop are the encoding and the oracle call. The encoding basically encodes the problem that asks a question: is there a model, say decision tree of size n, that respects our training data? And the model, as I said, can be anything, but the size, of course, can be also the number of rules, the number of literals, or the number of nodes, if we are talking about decision trees. And then after we have our formula, we can ask an oracle, is this formula satisfiable? If it says yes, then we can extract our model from the satisfying assignment. Otherwise, there is no such model, and we increase the size and proceed. At some point, we will stop when there is such a model of size m. Okay, the main problem of all these approaches is the encoding size, because if we target a large size of the model, and if our training data is large as well, and we know it's always the case, or most of the time it's the case, because we all care about big data for some reason, and these approaches just don't scale. The number of variables and constraints is too significant. So this year, there was an alternative approach proposed specifically for decision sets. I would like to mention it here. So instead of just considering that one-stage approach, the idea here is to divide the process into two stages. The first stage is to enumerate all possible individual rules. So recall, we're talking about decision sets. We enumerate individual rules here that can be done with the use of a discrete optimizer, for example, maxat, or MIP or CP. And the second stage is to, given all the rules that we have already enumerated, now try to compute a subset of those rules, to extract a subset such that it covers the entire training data. So this is reduced to the standard set cover problem, and it can also be solved using maxat or an ILP solver. And each class is computed independently here, which simplifies the problem further. The overall idea is, of course, to scale much better than before. Right? Let's see what stage one does. So each rule is enumerated as a call to a maxat solver, and the maxat solver is dealing with the partial CNF formula. So psi is a partial CNF formula. It is a conjunction of two parts, H and S. H is the hard clauses or hard constraints, and there are two types of hard constraints: coverage constraints, where we ask that each rule we compute must cover at least one instance in the training data of the right class. And the second type of constraints says that the rule we're computing must not cover any wrong instance, any instance of any of the wrong classes. And the soft constraints, basically, they just represent our preference to minimize the model. So we want to minimize the number of used literals in each rule. Okay, and here I just have the encoding size, but it really doesn't matter. I wanted to show that it's much smaller than before, and it should scale better. The second stage is, let's say we're focusing on class no, so the friend is not going with us for a date, and there are two instances for this class, and say that we have 4 rules that are given by the first stage. So we run our first stage. These are the rules. Now we can formulate the set cover problem this way. Basically, we are constructing a 0-1 matrix. The rows represent examples, and the columns represent rules. And we put a 1 there if the rule covers the corresponding example, and we put 0 otherwise. Now the problem is to minimize either the number of rules used or the total number of literals used, where we sum the size of each rule used, subject to constraints that enforce that each example in the training data must be covered by at least 1 rule. So this is the second stage, and that same approach also proposed symmetry breaking mechanism, because it can be noticed that for any example in the data set, there may be multiple rules that cover it. For example, if we look at example E4, there are 2 rules that cover it. Both are valid, and they don't cover anything else. In this regard, they can replace each other, right? And there is no point in computing both. In this case, we call these rules symmetric. And to forbid computing symmetric rules, we can compute 1, and then when it's done, we can add a clause. It's a single clause saying, next time, the next rule must cover something else. So this is a pretty cheap symmetry breaking technique, and it works well in practice. I have some results here. On the left, we have a cactus plot comparing the 2-phase approach against the 1-phase approach.
Might explain what a cactus plot is?
So the cactus plots, they show lines, and here on the x-axis we have the number of instances that are solved. On the y, we have the time limit. So this is the number of instances solved at most within this amount of time, right? For instance, here we have 700 instances solved within, I don't know, maybe 75 seconds. Okay, so we compare the two-phase approach against one-phase approach. This is the state of the art in the area. The approach that minimizes the number of rules is called MDS2. It's shown here. And the approach that minimizes the number of literals, which is a more fine-grained objective function, is shown here. It's called opt. So the latter problem is harder to solve. And these are various configurations of the two-phase approach. Okay, as you can observe, the best two configurations, actually this one minimizes the number of rules and this one minimizes the number of literals in the model, and they go hand in hand. So there is almost no difference, which is in clear contrast with this line and where is MDS2 in this line. So if we consider the one-stage approach, there is a huge difference. If we consider this two-stage approach, there is almost no difference. And if we look at the right-hand side of the plot, this is the scatter plot. So on the x, we show the time spent for a specific instance by one approach. On the y-axis, we show the time spent for the same instance by the other approach. As you can see here, the two-stage approach outperforms the competition by several orders of magnitude, which I think is quite significant. Now, the part on interpretability is now done. Let me talk about decision tree intrinsic interpretability and the myth of intrinsic interpretability. So here is a quote taken from one of the papers of Leo Breiman. He's the father of random forests. And the quote says, on interpretability, trees rate an A+. And it's not just an opinion of a single individual. So people really believe there is a common agreement that decision trees are one of the most interpretable models. And moreover, a lot of people argue that we should, in safety critical applications, we must replace black box models like neural networks with decision trees because they are much more interpretable. So what do they mean by intrinsic interpretability? Say we have this abstract decision tree. So we have some left subtree and right subtree. And I highlighted two paths here, right? The idea is that if we have an instance, and say in an instance we have m features, each feature receives a value. If we want to understand what prediction we get for this instance, basically we just check the path that fires the prediction, we execute this path, and an explanation that is given to us by default by this dt would be just take the literals that appear in the path. In this case, we have only 3 literals, ignore everything else, and that's your explanation, which is often good because it's a succinct conjunction of literals that appear in the path, and it's enough, right? The problem is that there are families of functions for which this default intrinsic interpretability fails. For instance, we have this function f. It's a DNF. Each term in a DNF contains 2 literals, and if, say, we have n equals 4, then we have 2 terms. One is x1 and x2, the other one is x3 and x4, right? And the smallest size decision tree for this for this function would be this. I emphasize this is the smallest size tree. There is nothing smaller than this. And say we have this instance 0, 1, 1, 1. Sorry, 1, 0, 1, 1. And this path is fired for this instance, right? So this path has 4 literals. That means that the explanation given to us by this dt would contain 4 literals. But in fact, we know what the function is. And we know that to make the DNF true, we can just make one of the terms true, right? And in this concrete case, the actual explanation that would be succinct includes only 2 literals. It's not a big issue here because we only have 4 variables. But imagine we have the same function for n equals 1000. In that case, we would have a path of length 1000, while the actual explanation would be still of size 2. That means that there are families of functions for which the path may be arbitrarily larger than the actual explanations, which may be a problem. So the conclusion here is that sometimes, not always, but sometimes decision trees aren't really interpretable. And it happens even for optimal trees, those that are guaranteed to be smallest size. I have a table here that shows some results that are obtained for a large number of data sets and for two well-known decision tree learners, including IAI, which means interpretable AI. They claim that the trees they learn are interpretable. And the other one is ITI. It's a well-known algorithm to learn decision trees. The most interesting columns here are percentage R and percentage C for both of the tools. Percentage R means the percentage of paths in the decision trees that are redundant. If you look at, for example, the car data set, and if you look at IAI, 86% of the paths are redundant in the DT, right? The percentage C column shows the fraction of the entire feature space that are covered by these paths. So in this case, it means that these paths, they cover 89% of all instances that exist out there, right? Only 11 instances get succinct explanations and 89% don't. The situation is worse for ITI. So IEI is not that bad. For ITI, it's even worse. Another interesting column is this average percentage of literals that can be dropped from a path. So we checked how many literals can be dropped to make a succinct explanation. And often it happens, even if we look again at the car data set, 45% of literals can be dropped on average from a path. It's not just one single literal that makes it redundant. It actually almost a half of the literals, right? Now, a similar issue appears to happen for decision lists, not to the same extent, because if we get an optimal decision list, then we don't have that problem. But if we use a heuristic algorithm, for example, CN2 or Reaper, we don't have any guarantees on the size of the decision list. In that case, we can have a similar problem. Again, we have a function which is the same, and we have a decision list. It's a valid one. It's not the smallest size, but it's a valid one. Again, we consider the same instance, and the rule 5 fires. It has 4 literals, but again, we know the nature of the function, and we know it's enough just to assign 2 literals to guarantee the prediction is going to be 1. Okay, okay. So I have talked I mentioned several times what actual explanations. What are these, and how do we get such explanations? Which brings me to the second half of my talk on computing post-hoc explanations. Here I should first say that there are heuristic approaches for this problem, including the most prominent one, Lime, Schaap, and Denker. They are extremely popular, and every day they appear more. They appear more I should say, every year probably hundreds or even thousands of papers appear in this area, and most of these approaches, they don't provide any correctness guarantees for the explanations they compute. They also don't provide any minimality guarantees, so we don't know if the explanations they compute are minimal. And the question is how reliable they are. I will get back to this after I talk about formal explanations. So let me talk about abductive explanation. So this work was done in 2018, and the intuition is like this. We have this complicated machine learning system. Let's say it's a neural network. The idea is that we can represent the classifier, the way it operates, as a first-order logic formula, for instance, formula M. We can also represent the input that it receives as a conjunction of individual literals. If we speak first-order logic, it's called a cube, right? For instance, it can be this pixel is black, and that pixel is red, and some other pixel is, I don't know, blue, and we consider a conjunction. Finally, the prediction can be seen as a single literal that says a class equals cat. We can give it an integer label, and we can say the class equals 1, for example. Right? If we have this, then we can represent the classification process using this entailment. So the model, if fed with some input, entails prediction pi. So when we have this, we can relate the problem of computing explanations as computing subsets of the input I, such that they are enough to entail the prediction pi. So this way, the problem is related to propositional abduction, hence the name of explanations is abductive explanation. Okay, let me give you a formal definition of this. Okay, so here we are in the realm of classifiers that compute total functions, which map instances in the feature space F to a class from some set of classes K, and we are interested in an instance V such that the class for this instance computed by our classifier is C, right? And an abductive explanation is a subset of features such that if we fix them to the values in the instance, then the prediction is not guaranteed to change for any instance in the feature space, right? So these explanations, they help us answer a why question. Why this prediction? Well, because these features are responsible for it. Somewhat dual concept is the concept of contrastive explanation, which is also a subset of features such that if we allow them to be free to take any value, then there may be an instance in the feature space which is predicted differently, even though all the other features take their values from the instance. So these explanations help us answer a why not question. I have a couple of examples here. Okay, let's say we have 5 features, each has the domain 0, 1, 2, and we have 2 classes, minus and plus. And this is our model. For simplicity, we consider decision lists, right? 3 rules only. And say we have an instance that assigns each feature to 1. Okay, now if we look at the decision list, it's easy to see that features 1, 2, they comprise an abductive explanation. Why? Well, because if we have x1 and x2 set to 1, then the first rule fires and we are guaranteed to have prediction minus. It's not that easy to see, but still possible to observe that if we, as long as we have feature 3 fixed to 1, rule 2 is guaranteed not to fire. And in that case, we also have the prediction minus. So we have another abductive explanation, which contains only one feature, feature x3, right? And contrastive explanations are 1, 3, and 2, 3, which means that we allow x1 and x3 take any value besides 1. Everything else is fixed to the instance, but as long as these are allowed to change values, then a misclassification can possible. So we're not guaranteed that the prediction minus is entailed anymore. Okay, and if you look carefully here into 2 sets, you can notice that there is a minimal heading set duality between the sets of contrastive and abductive explanations, which means that each contrastive explanation is a minimal heading set of the complete set of abductive explanations, and the other way around. Each abductive explanation is a minimal heading set of the contrastive explanations. I have another example here. Say we have 5 features, but they are Boolean this time, and we have a binary classification. This is a decision set represented by a DNF. So this DNF has 4 terms. Each term has 3 literals. And say we have this instance that assigns everything to 1. The class is 1 this time. Of course, it's easy to see that as long as x1 and x2 are set to 1, then either term 1 or term 2 are evaluated to 1, and then the prediction is going to be 1. So this gives us the first abductive explanation. Similarly, if we assign x1 and x3 to 1, then one of the terms t3 or t4 take the value 1, and then we are still guaranteed to have our prediction 1. So these are abductive explanations, and we can actually compute contrastive explanations by computing the minimal heading sets of these 2 abductive explanations, and we get we can see that as long as we allow x1 to take any value, which means it can take a value 0, then the prediction can change, so it can become 0. And similarly, if we allow 2 and 3 take any values, then the prediction can also change, so our classifier takes value 0. How do we compute these explanations? Well, I should say here that the AXP and CXP conditions that appear in the definitions, I will show them later again, they are monotone with respect to set inclusion. It means that if we want to get something subset minimal, then we can check if the condition holds for a given subset set of features, and then we can also check if it holds for all the proper subsets. Right? This is what this note says. We can check the predicate, the condition for our current subset, and also check that it doesn't hold for any proper subsets. And the overall approach is like this. We encode the classifier into some suitable logic for formalism. It can be a propositional formula, it can be a CP program, it can be a MIP program, it can be something. And then we we start from the complete set of features, and then we simply traverse all the features and we try to drop them and check if our AXP condition holds. And this is the condition, right? And for CXPs, it's very similar. We start from the complete set of features and we drop them one by one and check the CXP condition. And we proceed until we traverse all the features, right? Here I have an example. Again, our decision list, and say our instance that is there's a negative class. So why negative? Well, what we do is we try to drop the first feature and we ask, is it still guaranteed that the prediction is minus? Meaning that can we drop this feature? Yes, we can, because we are sure that the prediction is still minus. Can we drop feature 2? Yes. Now, can we drop feature 3? Well, no, because if we allow it to take any value, then it may happen that the second rule fires. We continue, we check the fourth feature, the fifth feature, and then we get an answer. This is an abductive explanation which contains just one feature, right? Similarly, for contrastive explanations, we consider the same instance and we ask the question, why not plus, right? Well, we traverse our set of features and we try to drop them one by one again. Here, dropping means that we fix the feature to the value in the instance. Otherwise, if it's in the explanation, it can take any value, right? So can we drop feature 1, meaning that can we fix it such that the prediction can still be different? And says, yes, we can drop it. Can we drop feature 2? Well, no, because if we drop both of them, that means that we fix them to 1, then the first rule fires. We are not guaranteed. We can't get a misclassification anymore. So that is necessary, right? Similarly, we check the third feature. We can't drop it, but we can drop feature 4 and feature 5. And this gives us a contrastive explanation. And this is the general pseudocode. We start from the complete set of features, and then we traverse all of them. At each iteration of the slope, we check if dropping the feature doesn't change our results. We're still guaranteed to have an AXP or CXP. If it's the case, we drop the feature for good. Otherwise, we put it back. In the end, we have either abductive or contrastive explanation, depending on the predicate, on the condition we check. Okay? As you can see, this is a very simple deletion-based linear search. It does the number of oracle calls equal to the number of features. But if we want to reduce the number of oracle calls, we can try to use something more sophisticated like quick explain or progression. The key issue here is how hard it is to reason about how to make that oracle call. Okay, and what was shown recently that for some models, extraction of a formal explanation can be done in polynomial time. And this holds for naive Bayes classifiers, for decision trees, for graph-based classifiers, and for monotonic classifiers as well. But in general, what we have to do, as I mentioned before, we have to encode our model into a suitable logic formalism. It can be SAT, SMT, MIP, PB, CP. And then we basically apply that linear search of quick explain with the corresponding reasoner for that logic. And depending on the logic we use, the performance may vary a lot. So we saw that in practice. Let's consider a concrete example of neural networks, because neural networks is everything these days. I'm not an expert in neural networks, but I will just give you a basic idea. So a neural network is a sequence of interconnected layers, except for the first input layer and the output layer. The hidden layers are all of the same structure. They can be seen as a block. And there is the same kind of computation used to get the values in each block. Right? Basically, it's just a matrix of weights multiplied by some input vector x plus some bias vector b, on top of which we apply an activation function to see if these neurons fire or not. Right? And there can be multiple activation functions. And here we consider ReLU activation functions, which is rectify linear unit. This is a piecewise linear function shown here. Okay. This is the algebraic representation of a computation of one block. So as I said, we compute the vector x prime as the matrix A multiplied by x and plus bias vector b. And then we apply ReLU activation and we compute the values of y. And on the bottom of the slide, I have the encoding, which was not proposed by us. It's an own encoding proposed by Fischetti in 2016. It's a MIP formulation. So we have a linear program here. And the key feature here is that they propose to use indicator variable Z here to handle ReLU units. I have an example here. Say we have this very simple neural network. And here's what it computes. This part shows the truth table. As you can observe, actually, this neural network computes a simple disjunction. So the output equals x1 or x2. So the weights for x1 and x2 are both +1 and the bias is -1. And this is how it's computed. This is the computation. The output is computed as the if-then else operator. Because we have only two classes, there is no need to apply any sophisticated probabilistic reasoning here. Okay. If y is positive, then the class is 1, otherwise it's 0. And here is the Fischetti's encoding. Now let's consider instance 1, 0. That means x1 is 1 and x2 is 0. The class must be 1. And this is what we get if we call a MIP solver. Given this instance, it will say that the output value is 1 indeed. Okay. Now, the algorithm I outlined before would try to traverse each feature, try to drop it, and see if a misclassification is possible. So let's see how it works. So we have x1 equals 1, and we try to drop it. So we need to check if we can get a misclassification. The only possibility for us to drop feature x is to assign it to value 0 instead of 1, right? Because we are in the Boolean domain. And though if we call a MIP solver, it will say, okay, the class will actually become 0. If we consider this instance, the class changes from 1 to 0. It means that x1 is necessary to keep, otherwise we can reach a misclassification. So we put it back and we check the second feature. Is it possible to drop feature x2? Well, the only possibility to drop feature x2 is to assign it to 1 instead of 0. In this case, we call a MIP solver again, and it says, okay, now there is no misclassification. The output is 1, which means that dropping x2 doesn't change anything. So it can be dropped, and the explanation we get in the end would be containing just the one feature x1. And this table shows some results we got in 2019 for neural networks for some of the data sets. I should say that this was the first formal approach to explaining neural networks, and the scalability is not best, so it leaves somewhat much to be desired, because we were able to explain only neural networks having just a few dozens of neurons, which is not great. But we were able to run SMT solvers and MIP solvers back in 2018, and what we observed is that MIP is much better than SMT. So we tried Cplex and we tried a lot of SMT solvers, and all SMT solvers were significantly outperformed by MIP. We also showed that we can compute subset minimal explanations the way I explained before using the simple linear search, but we can also compute smallest size explanations, which is much harder problem. So here the performance, as you can see, we can't compute anything here, which is not the case for subset minimal explanations. Okay, here I have the efficacy map showing how hard it is to compute explanations for different families of classifiers. As I mentioned before, some classifiers like naive Bayes, decision trees, and other graph-based classifiers, as well as monotonic classifiers, are here, which means that explanations can be computed in polynomial time, and in practice this is very efficient. But in general, the problem is hard for DP. Even in that case, for random forests and for decision lists, we are in the realm of propositional logic. So we can reduce the problem, we can encode it into propositional logic and use very efficient SAT solvers. And because of that, we can compute explanations quite efficiently. It's a bit worse, but still efficient for boosted trees, where we can apply SMT solvers or MIP solvers. But the current status quo is that for neural networks, it's really hard to compute explanations. As I mentioned before, we can only handle neural networks up to a few dozens of neurons, which is not great. For Bayesian classifiers, it's even worse, because we need to reason about probabilities, and we need to multiply probabilities, and it's really hard. Even if we use MIP, actually, I don't think we can use MIP, but we can apply CP, and it's hard for CP. So what next? Is there any other way we can use logic in this area? Well, we can actually try to apply logic to assess the correctness and precision of heuristic explanations. Let's say we have this boosted tree. It's trained on the well-known zoo animal classification dataset. It's a valid boosted tree. Each tree assigns weights for each of the 7 classes. And the winning class is the one with the highest weight. And say we have this instance. This boosted tree says this animal is a reptile. Okay. Now, if we want to explain why it's a reptile, we can run a heuristic explainer, for example, anchor. And anchor says, well, it's reptile because it doesn't have hair, doesn't have milk, there is no teeth as well, no fins. That's why it's reptile. But we can apply logic and we can extract a counterexample instance that has these same features assigned the same way as in the explanation. So this instance has no hair, no milk, no teeth, no fins, but the class now is amphibian according to the model. So how can we do this? Well, this is actually pretty simple, right? We have our heuristic explanation H. What we need to do is we need to check satisfiability of this formula. So this formula says that there is an instance in the feature space such that the values of the features are exactly the same way as in the explanation, but the prediction is different. Okay, and if we're careful enough, we can see that this formula is actually the negation of the AXP condition. So basically, we can check the correctness of explanation by checking if it's an AXP or not. And I should say that there may be multiple instances like this, not just one. Okay. What we can also do using logic is, given an incorrect explanation, we can try to repair it. So this is what we did, and in that concrete case, we can make minimal changes to the explanation such that it becomes bulletproof, so it becomes correct. We can also try to reduce explanations further if they are not minimal. So in general, we did this experiment. Given a heuristic explanation, we check its validity. If it's not valid, we try to repair it, and we report it to be incorrect. Otherwise, we try to reduce it further. And if we succeed, then we say the explanation is redundant. Otherwise, it's perfectly correct and minimal. And this is the result of the experiment. So we considered 5 well-known data sets studied in the context of explainability, but also in the context of fairness. And we used these 3 most popular heuristic explainers, Lime, Anchor, and Chubb. As you can see, the percentage of incorrect explanations is quite large for all these explainers. So, for instance, if we look at the recidivism data set, it's row 3, we see that Anchor computes more than 99% of explanations incorrectly, right? The situation is not much better for Lime and Chubb, which is also interesting that Anchor is actually quite good at minimizing explanations. We were unable to minimize too many of them, but it's not the case for Lime and Chubb. So they compute either something incorrect or redundant. And for some of the data sets, for lending, for example, it's a bit surprising, but it's a fact. All these approaches work quite well. So quite a large number of explanations computed are correct and minimal. This is not yet explained, but yes, this is what we observe. So given this result, the question is whether we should trust heuristic approaches or not, or maybe we should try to rely on logic. Well, we didn't stop there, so we tried to go further and check how many counterexamples there exist, right? Before, in the experiment I showed before, what we saw is that if we have an explanation, there is at least one counterexample. Now, the next step we did is we tried to assess approximately how many counterexamples are there given an explanation, right? So we actually tried to approximately compute the number of models of this formula. And we did 2 experiments. One experiment is shown on the left and the other is shown on the right. On the left, we have the unconstrained feature space. This means that we allowed counterexamples to be anywhere. And in the right-hand side, we see the result of the experiment where we allowed counterexamples to be at most 50% different from the instance that we are explaining. This way, we try to be close to the instance, so we try to help Anchor. And we ran Anchor to compute heuristic explanations. Anchor is able to assess its own precision, and it's kind of over-optimistic. It always says that its explanations are 99% correct. And according to our results, where we used the state-of-the-art, at that point it was the state-of-the-art in the area, approx MC, and our results are much worse for Anchor. And what we observed is that the accuracy is actually not that great. It was 20 to 25% less than what Anchor says. Okay. I think this summarizes my talk. I should say again that XAI is vital. Hopefully, I convinced everyone that it's important. And hopefully, I also managed to convince most of you that there is a lot of use cases for logic in explainable AI. It can be used to compute interpretable models. It can also be used to compute formal explanations that are guaranteed to be correct and minimal. Logic can be used to reason about the correctness of heuristic explanations, because heuristic explanations are great in terms of scalability, but they aren't great in terms of correctness. So we can try to repair them or minimize them. I didn't talk about this today, but the area of verification of machine learning models exists, and it's huge. And there, people also use logic, and all the reasons that exist out there. There are lots of challenges for logic in explainable AI. There are many of them. I mentioned just a couple because I think these are the most interesting ones. First of all, well, there is, of course, the scalability issue, right? Because we apply reasoning and we apply solvers, and that means that we are at the mercy of their power and expressivity. So it means that, as I mentioned before, for neural networks, we can't do much. And this basically, hopefully, motivates the need for better solvers that are designed to reason about machine learning models. The second issue is that, which we observed in practice, is that not all explanations are equally good. So we can apply logic. I didn't mention this today, but we can apply logic to enumerate all explanations, not just to compute one, but we can enumerate, I don't know, 10, 100, or all of them exhaustively. And not all of them will be interesting for a user. This creates two directions of work. One is constraint explanations, where one is interested to compute explanations subject to some background knowledge about the universe that exists out there. If it's given, we can apply that knowledge to compute more meaningful explanations. And there is some initial effort in this direction by the people in Sydney. The second line of work is to compute preferred explanations. This means if a user wants this explanation instead of that one, I don't know, symmetric explanation or some explanation that has some specific syntactic properties. So we need mechanisms to compute these kind of explanations. And this is not yet covered, at least to the best of my knowledge. I think there is nothing done in this area. And finally, even though we can compute explanations that are correct, that they really reveal what is happening underneath, under the hood of this machine learning model, it's not yet clear how we can use this knowledge to repair our model if, for example, it behaves incorrectly. We see that it does something wrong, but how do we take it into account? This is not yet done, and I think this is a pretty interesting area of work. That's it for me. Thank you very much. I will be happy to answer questions if there are any.